So this is going to be part one of parallel programming in Chpl. My name is Alex Razumov, and I'm with Westgrid. I'm a Westgrid training and visualization coordinator. So why Chpl? Why we decided to teach Chpl in this session? Well, so Chpl is a parallel programming language that was designed by Cray at Cray. It's an open source language, so it's not limited by any means to Cray computers only. It can actually run on any Unix-like platform. You can run it on your laptop, you can run it on a big memory server, you can run it on an HPC cluster. And when they were designing Chpl, the goal was, on one hand, to write a language that will be very high level, that will be as easy to program in and understand as, let's say, Python or Matlab. And on the other hand, they really wanted to have a good performance. So performance, the code written in Chpl should be fast. So it should perform as well as a compiled and optimized code written, let's say, in C and Fortran. And also, a big part of Chpl is that it's a parallel programming language. So there are built-in abstractions for task parallelism and for data parallelism. So by task parallelism, I mean the ability to launch additional threads or additional tasks and then do some computation in these tasks. So for example, you can launch one task to do some computation, then launch another task on the same node or different node to do another computation, and so on. And have really full control over when, how, and where you launch these tasks. And also data parallelism. So I'm getting noise from somebody, so please make sure to mute yourself. Thank you. And also data parallelism. So data parallelism is basically means if you have some data structure or an array, and you want to distribute this array among several compute nodes, you can do it very easily in Chpl. And also the beauty of Chpl is that when you have a distributed data structure that spans several compute nodes, then computation in Chpl will also be optimized. So we'll try to follow the data structure. So if you have some computational stencil where you're using some elements that are sitting on remote node B, then a computation will likely be happening on the node B as well. So it's really optimized in that sense, that computation follows the data structures. And also I should mention that Chpl is designed around what they call a multi-resolution philosophy. So it's very easy to start to do parallel programming in Chpl. So typically a few lines of Chpl code, well, few lines of Chpl code that have a parallelism, they replace tons of lines of MPI code, message passing interface code. So message passing interface, for those of you who don't know, it has been an industry standard for parallel programming on distributed memory architectures for about 20 years, and the idea in MPI is to pass messages. So in Chpl, you don't pass messages explicitly. Instead, you work with these paradigms of data parallelism and task parallelism, and it's really easy to write fairly complex Chpl codes. But if you want to have more control, you can certainly dig deeper and bring your code down to the machine or close to the machine level, so that it can actually get the very last bit of performance and full control over your code. So that's called multi-resolution philosophy. Because Chpl is so Chpl strives to achieve the same performance as an optimized C or Fortran code. It is a compiled or compilable language. So that means that you write a text file typically with extension .chpl, and then you store your code in that file, and then you compile the file, maybe you optimize it optionally, and then you run the code on the computer. So all links, by the way, as you just saw in my slides, they are clickable. So I just accidentally opened the link. Because of this ease of use, Chpl is really a perfect language for learning parallel programming for beginners. And so traditionally in Westgrid and Compute Canada, we've been teaching MPI for distributed memory parallelism and OpenMP for shared memory parallelism. So the goal of Chpl is to really replace both. And I think Chpl is really fantastic for learning parallel programming if you don't know anything about it, simply because it's so much easier and it's so much higher level than MPI, let's say. So I already mentioned that Chpl is open source, so you can compile and run it on all Unix-like platforms. It's actually fairly easy to get it compiled. The Chpl community is fairly small at the moment, and unfortunately, this is kind of a chicken and egg situation because so few people use Chpl. So it's a small but very passionate community, but fairly small fraction of HPC users use Chpl on a regular basis. And because so few people use and know about it, not too many HPC centers install it on their machines, and especially teach and try to popularize Chpl. And because of that, well, not that many people use it. And so hopefully that's going to change in the next few years. And well, we're trying to change it now with these tutorials. So in the next slide, I collected a few Chpl links that you may find useful. So there are some useful slides at the Chpl language website, so chpl-lang.org, covering data parallelism, task parallelism, concepts of locality and domain maps, and so on. And there's also a very nice Chpl presentation by one of the Chpl creators, Brad Chapelain. So it's on YouTube. If you're interested in getting, a more intimate look at the language and the ideas behind the language, then this is a very good presentation. A Getting Started Guide for Python Programmers, Learn Chpl in Y Minutes. So this guide, Learn Chpl in Y Minutes, is actually really nice, but it mostly covers not parallel concepts, but just the basic language features, and a few other tutorials. So I should also mention that when you install Chpl, and the same applies for Cedar installation, every time you install Chpl, in the directories, you also have, well, inside the Chpl installation directories, you also have the full documentation of Chpl. So if you go into this directory, Chpl home modules, and then there are two subdirectories, standard or this, you will see lots of examples and full documentation there as well. So our workshop is a three-part workshop. As I mentioned, it's meant to be interactive, so feel free to stop me at any time. And today we're going to cover the basic language features. So we'll be doing lots of coding, but you will not see any parallel code today. So today we'll just cover the basic non-parallel language features, and we'll learn how to run, to compile and run Chpl programs on Cedar, Cedar Supercomputer, and then I will walk you through the problem that we'll be solving in our code. So it's going to be two-dimensional heat transfer problem. So we'll cover basic things like how to initialize variables, the type of variables you can have in Chpl, ranges, arrays, conditionals, for loops, timing code execution, and I think that will actually fill up most of the next an hour and a half, I guess. So I already mentioned that we have collaborative nodes at the following address, so bit.ly/chpl1. And this is meant to be editable by everybody. So if you have any question, or if you want to paste the code, or anything you want to share, feel free to add lines of text to the page. And next week, we're going to cover task parallelism. So today, we're going to run only single core, not parallel codes, only serial single core codes. So next week, we'll be running shared memory codes in Chpl. So all codes, well, you're using several CPUs on a single node. And then in 2 weeks, on March 14th, we'll do domain parallelism, and we'll be running distributed memory codes in Chpl, and also hybrid codes, combining both distributed memory parallelism, so data parallelism, and task parallelism on a single node. Okay, any questions at this point? If not, then let me jump to, so let me move out some windows out of the way. And I will jump into my programming environment. So here on the left, I have the text editor, and I'll actually open it on another file. So the file is currently empty. I will start coding from scratch. But before that, let me log in. So on the right, I have the terminal, and I will log into Cedar cluster. So here I'm on the login node of Cedar. And to actually use Chpl, you need to load the right module. So what you can do is, if you type module, spider, and then Chpl, that will give you a lot of information, but basically it will list two modules. So one of them is going to be a multi-locale Chpl module. The other one is a single locale Chpl module. So we're going to use the single locale Chpl module today for running for running serial codes. Locale is the concept in Chpl that essentially refers to a compute node. So a single locale means a single compute node. Okay, so to load that module, you have to type module load GCC and then the name of the single locale Chpl module. So that's the command line. And you see, by the way, so if there are any problems, you cannot see the fonts or stuff is truncated, let me know. So if I don't hear anything, I assume you can see everything on my screen. So here at the bottom, I'm typing the command module load GCC, and then the name of the Chpl module. So you need to load the GCC module because Chpl actually compiles to C code, and then that C code compiles to machine executable. Okay, so we need to load both the C module and the Chpl module. Okay, so now it's done, and if I do module list, it actually shows me what modules are loaded, and you can see that GCC and Chpl single module are part of the of that list. So now if I type the command chpl, that calls the compiler, and just hit enter. I didn't pass any file name to it, so you see that it basically shows me the basic help page. So all the flags you can pass to the compile command. So once again, the compile command is chpl. So let's try to run, write, compile, and run a very simple Chpl code. So I'm going to go into a temporary directory. You can just cd into any directory on Cedar. And so here I have a file. On the left, I have the text editor. So I'm going to write a very simple code in Chpl. So I'm going to say write ln, write line, and then I will say if you can see this, everything works. If you can see this, everything works. Okay, so put it in quotes, close the brackets, and then at the end, you always need to have a semicolon at the end of each Chpl command. Okay, so now let's try to compile it. So I'm going to clean my screen, and I'm going to say Chpl, then the name of the code. So in my case, is test.chpl, and then optionally I can specify the executable name. So it's going to compile into an executable called test. And it should take a couple of seconds. So here we go. Now we have, if I do ls, you can see that in green, I have the executable test, and then I simply run it, and then you can see the output. So if you can see this, everything works. And the code is very simple. So we didn't initialize any variables, it's just a print statement. So write line, simply, there's also a write statement in Chpl. So write without the ln line will not give you the end of line return character. So you will see what I mean. So if you compile it again and run it, it will simply not give the end of line character at the very end, as you can see. Okay, so that's the only difference between write and write ln commands. Okay, so right now what we did, we compiled the code and ran it right on the login node. And this is fine as long as you're doing some very simple serial testing. So you have to be, with Chpl, you have to be really, really careful about this on Cedar, simply because if you try to run a parallel code on the login node, well, if you try to run a code that multi-locale code that's supposed to span several compute nodes, like this on the login node, then you'll get actually an error message. If you try to run a single locale, so single node, parallel code, so by parallel I mean code that will try to utilize more than one CPU core, you'll be able to do that on the login node, but it's a very good idea not to do this because so I don't know how many people we have here, so maybe with web streaming we have maybe 20 plus people here. So if everybody tries to do to run a parallel code on the Cedar login node, most likely we'll see problems. So people will use many CPUs at the same time, and it's just not a good idea to do because well, a login node is a shared resource. So next week and the following week, when we'll run parallel codes, we'll actually do it inside a reservation, submitting compute jobs. So today we're fine because we'll be running only serial codes and we'll be running only very short codes. So we can just do it on a login node. If, on the other hand, you want to do work today inside an interactive compute job on a compute node, you certainly can do that. So you can submit a job. So I'm going to show you how to do it. So you can submit an interactive job using the salvo command. And then you can specify time. Let's say I want to ask for a single core for 30 minutes. So here we go, 0 hours, 30 minutes, 0 seconds. And then you can specify memory per CPU. So I'm going to ask for 1,000 megabytes. And then if I run this command, it will actually give me an error message because I did not specify the account name under which I'm going to run this interactive job. So you see that I get an error message, and it says that you need to specify the account. And for each one of you, it's going to be something different. So for me, it actually gave me a hint. I need to use the -- account. In my case, I have to specify my default account, which is allocation, which is this one. But then for each one of you, it's going to be something different. So don't copy the entire command. The last argument is going to change for you, right? So the last argument should match your default allocation on Cedar, okay? And then -- account, I mistyped it, so it should be account. And then it will try to start an interactive job on one of the interactive nodes in Cedar. We have several such nodes. And usually they're idle. They're meant for quick testing, for debugging, but not for running production jobs. So once the jobs get started, I will get a prompt on the interactive node where it gets started. So that can take a few seconds. That can take a few minutes, depending on, well, how busy the schedule is and how busy the interactive nodes are. So let's just wait and see if it gets started. Because today we're not using a reservation, so it might actually, if these nodes are busy, it might actually take a little bit of time. I'll wait a few more seconds, and then if it doesn't start, I'll just cancel it and go back to the login. Okay, well, it doesn't start, so I'll just cancel it, and we'll continue running on the login node. And for some reason, the scheduler is busy. I don't know what it's doing, but I cannot even cancel my submitted job, which is highly peculiar. Okay, so I'm going to kill that. All right, and we'll start from scratch. Today we're going to be solving the heat transfer problem. So let me go back to my slides. And this is the basic problem. So if you've never seen the heat diffusion problem, don't be scared. I'm going to show you a much simpler equation very soon. Imagine a metallic plate initially at 25 degrees everywhere, two-dimensional plate. And then this is the diffusion equation we're going to solve. So the time derivative of temperature, capital T is temperature, is simply equal to the Laplacian of temperature. So we're going to discretize this differential equation with T, N, I, J. So N refers to the time step, and IJ refers to the rows and columns respectively. So the upper left corner is 1, 1. And the size of the problem is going to be rows by calls. So the lower right corner is rows calls. So initial condition, as I mentioned, 25 degrees. And then we're going to apply, not at first, but eventually we're going to apply the following boundary conditions. So upper side and left side of this two-dimensional plate are going to be sitting at zeros. And then the bottom side and the right side are going to have temperature that linearly increases from 0 to 80 degrees according to this formula. So we'll discretize our differential equation. So we'll substitute with the finite difference equation using forward early time stepping. So on the left you have the time derivative, and then discretized time derivative. On the right you have the discretized Laplacian. And then we assume we simply use of simplicity the same grid spacing in both x and y, simply equal to 1, and then use a uniform time step equal to 1/4. And then if you plug in these values back into the last equation, and then write the expression for the temperature at step n plus 1, then this is the expression you will see. So basically, the temperature at the next time step at every point is simply going to be the average of the temperatures at the 4 surrounding points. So that's our compute stencil. The points I plus 1j, I minus 1j, ij plus 1, and ij minus 1. So really, really easy computation. So our task is to, knowing the temperature at the current time step, so initially it's 25 degrees, to find the temperature in the next time step and then iterate for a certain number of iterations or when the system is in steady state. And of course, it's going to go to steady state simply because we have this temperature differential. So on the left side and upper side, we have zeros. And then on the right side, we have non-zeros temperature. So eventually, the distribution will come to a steady state. And let me switch to a new file that I'm going to call basesolver.chpl. So this is where I'm going to be writing my code. And before I start writing Chpl code, I want to paste in the, type in the actual computation that we're going to be doing. And then I'm going to comment it out. But I just want to type it now so that you all see what the formula looks like. So it's T new is the temperature at the new time step is equal to 1/4 of the following sum. So T I minus 1j plus T I plus 1j plus temperature at ij minus 1 plus temperature at ij plus 1. Okay. So here we go. And I'm going to comment this out. So the comments in Chpl are very similar to comments in C or C++. You simply have the two forward slashes, and everything to the right from it is going to be a comment. Okay. So we have right now an empty code with a single comment line. Okay. So our objective is to write a code to implement the difference equation that you saw, and the code should have the following requirements. It should work for any given number of rows or columns in the grid, so the problem size, the matrix size. It should run for a given number of iterations, or until the difference between the new temperature, T new, and the current temperature, the old temperature, T, is smaller than a given tolerance. And the code should output the temperature at a desired position on the grid every given number of iterations. So today we're going to write the serial code. We'll try to optimize it, and we'll play with the problem size and a few other things. And then next week, we're going to use task parallelism to improve the performance of the code and run it on a single cluster node. And then in 2 weeks, we're going to do use task parallelism to improve the performance of the code and run it on multiple cluster nodes using hybrid parallelism. Okay, so now we need to define some variables. A variable in Chpl, like in most programming languages, has 3 elements: a name, a type, and a value. So in Chpl, the types, the popular variable types are integer, real, logical, or Boolean, which is called bool, and then the string variable, right? So the common 4 types that you typically use in most programs. So by default, I can't remember the precision of integer and real. I should actually double check that, but optionally you can specify the precision. So look up the syntax for that. We're not going to specify precision today, so we'll just use the default either 4-byte or 8-byte precision for integer and reals. Okay. So to specify a variable, well, to initialize a variable in Chpl, you need to either define its type or give it a value, and then its type will be inferred from its value. Or you can do both, specify the variable type and the initial value. So let's define some variables. So first we're going to define several constant variables. So constant variable is a variable that is not going to change as the code runs, right? It's just a constant. So we're going to define number of rows. Let's start with 100 by 100 matrix size. So 100 rows and 100 columns. Okay. And this is just number of rows and columns in our matrix. Then I'm going to specify number of iterations. And let's just use maximum number of iterations, 500. Oops, I need a single semicolon there. So maximum number of iterations. And then I'm going to specify the position of the point at which we're going to output temperature. So I'm going to say constant, and I'll just call it I out. Let's say 50, somewhere in the middle, and then J out is equal to 50 as well. So, and this is some row and column numbers. Okay. So here we specified constant integer variables. We did not define their types, but we assigned values. And from the values, the type of values, Chpl sees that, okay, these are integer variables because we pass the integer values, right? So the inferred type is integer. On the other hand, we can define a variable just using its type. So let's define a variable, and now we're using the var keyword, so as opposed to constant. So this variable is going to be changing as we run the code. So we'll call it delta, and it's of type real. So we're not assigning any value, and when you're not assigning any value, by default it's going to be 0. But right now we're just defining the type. So this is the greatest temperature difference. Difference between t new and t at any time step. So for one iteration to next. And also let's define a temporary variable that we'll use for several things. So this is for storing temporary results. Okay, both are real variables, right? Either single precision or double precision. I can't remember before. And then let's define tolerance. So for tolerance, actually we'll specify both the type and its value. So I'm going to say constant. It's a constant variable, so tolerance is not going to change as we run the code. So constant tolerance, and let's just say 10 to the minus 4. So I can either do it this way and then say real, or I can use the scientific notation. Right? So I can do something like this: 1 times 10 to the minus 4. Right? So the usual programming notation for 10 to the minus 4. And so this is temperature difference tolerance. Okay? So in this case, you see that syntax is not immediately obvious, but this is the syntax used by Chpl. So variable type, not variable type, I mean either constant or variable, then variable name is equal to the value, then column, and then the type. That's the way you specify this in Chpl. Also, let's have a variable for iteration counter. So we'll initialize it explicitly to 0. We don't have to, but we'll do it. And it's of type integer. And then that's the iteration counter. And also, let's print out iterations every 20 number of time steps. So that's also an integer variable. So we'll say t of I out, j out will be printed every n out steps or iterations. Okay. So here I save my code. And by the way, if you're working on Cedar, so notice that I'm writing the code in standalone text editor. So this is Emacs, but the nice feature of Emacs, I'm running Emacs right on my laptop. It's a local application, but from Emacs, I can actually open a remote file, and the file is stored on Cedar, as you can see under my account, cedar.computecanada.ca, right here at the bottom. And in my home directory /tmp basesolver.chpl. So if you're not familiar with Emacs, what you can do is you can when you log into Cedar, you can open Nano, for example, Nano, and then pass the file name to it, and then you can actually work inside the terminal, and you can write a code this way, right? And then you can save it. So in Nano, let me open Nano again. So in Nano, the contextual menu is at the bottom. So if you press, for example, Control X, it will exit. If you press Control O, it will write out or save the file, and a few other things, right? So to exit, let's say we edit something in the code, and then I press Control X to exit, and then I save modified buffer. I say yes, and then I need to confirm the file name, hit return, and then here is my saved file. So I just inserted an empty line in there. Right? So this is an example of how you can edit a file directly on Cedar. I'm doing it on inside Emacs on my laptop, simply because this is way more convenient. I'm using a local text editor for saving a remote file.
Alex, sorry, in the fifth line, you forgot J out. So it's just J.
Oh, yes. Yes, thank you. Thank you. I need to edit it. So constant, yeah, right here, J out. Thank you. Yes. Right, so we specify tolerance, iteration counter, and out, delta, temperature, and rows, columns, number of iterations, I out, and J out. And then I'm going to add a simple line. So right line, working with a matrix, and then I'll just print the problem size and number of iterations and the tolerance. So working with a matrix, and then print out the number of rows, and then times number of columns, and then 2 number of iterations, and then say iterations, or dt temperature difference below, and then tolerance. Okay, so let me try to compile it. And again, to compile it, I simply say Chpl, the name of the file, and then minus -o, and then the name of the executable. And for simplicity, I'll just use the same base name, base solver for the executable. So if I don't have any any typos, it should be able to compile it, compiled, and then let's try to run it. And here we go. So working with the matrix size, 100 by 100 to 500 iterations, or dt temperature difference below 10 to the -4. This is, when we compile the Chpl code this way, this is not an optimized Chpl code. So it'll actually run slowly. If you want to add optimization flag, the option for that is --fast, and then it'll take a little bit longer to compile, but the compiler will try to optimize it a lot. And actually, the last exercise today, you will compare the performance of a non-optimized to an optimized code and see how much the performance differs. And then we can run the code again. When run, because it's a very simple code, when you run it, it'll just going to be the same output, so you won't see any difference. Okay. So now let's jump to any questions at this point. Okay, so let's continue. We will jump now to ranges and arrays. So in Chpl, there's a concept of the index range. So for example, if you have a range of numbers, let's say integer numbers from 1 to 5, the way you implement that, you write that in Chpl is 1, so left bound, dot, dot, and then the right bound. So this notation, 1 dot dot 5, simply gives you a range of integer numbers from 1 to 5. So ranges are useful for a number of things, for example, for doing for loops, and also for initializing arrays. So I'm going to show you an example. Let's define a variable for temperature, so capital T, variable T, and it's going to be an array. So it's going to be a two-dimensional array with the following range of indices. So row is going to go from 0, dot, dot, rows plus 1, and then columns going to go from 0, dot, dot, columns plus 1. Okay? And then we'll specify type real, semicolon, and these are our current temperatures. So this is a two-dimensional array of temperatures, and the size of the array is obviously, I'll just type it here, rows plus 2 times columns plus 2, right? So that's the size of the array. And the indices go from 0 to to rows plus 1 and columns plus 1. And this is the nice feature of Chpl is, unlike traditional programming languages where indices start from, by default start from 0, or from like in Python, in C, or from 1 like in Fortran. In Chpl, actually, there is no default starting range, starting index. It's whatever you specify. So in this case, indices will start from 0. Okay, and then to actually access the elements of this array, to access, let's say, the very first row, very first column, you will type something like this. So that's the very first element of the array. So T00 is the first row, first column. If you want to access, let's say, if you type 3, 7, that will give you the 4th row and the 8th column. And then, of course, you can also access, let's say, a row or a column or a specific subset of indices. Let's say if you type T2, 3, dot 15, that will give you elements in the 3rd row from columns 4 to 16. And then if you do similar for rows, you can say, let's say, 0, dot 3. And then 4 will give you column 4 and rows, column 5 and rows 1 till 4. Okay. So we're also going to specify another variable for storing new temperatures. So I'm just going to call it TNew. And it's going to have exactly the same dimensions. I'm just going to copy and paste it here. So rows from 0 to rows plus 1 for rows, and 0 to columns plus 1 for columns, and then same type real. And these are going to be newly computed temperatures. Okay. And by the way, I'm going to share the entire code. If you're trying to write down everything you see on the screen, you don't have to do it. You can if you want to follow along. But we'll also share the entire code at the end of today's session. I will simply copy and paste it into the collaborative notes. And also, I will give you a link to all my notes for today's session. So everything I say and everything I type, you will be able to see in those notes as well. So I will paste that into the Google Doc at the end of today's session. So
Alex,
we defined.
There were a couple of questions there on the chat.
Where are the questions?
On the chat there, on the group chat.
Oh, on the group chat. I minimized my windows, so I'll try to. I have so many windows right now. So,
about last element in the.
If you could write it for me, because I cannot right now when I turn on screen sharing, I have a minimized view and I cannot unminimize it, and I don't see the screen.
So the last question was if we can access the last index element in the array with a -1, like in Python.
No, I don't think so. I haven't tried that, but I didn't see this notation, so I really doubt it. So I think for the last element, you actually have to specify the value of that element. I don't think -1. I've never seen it, so I doubt it will work. What's the other question?
There was another question. If the indexing starts with 1 or 0 in Chpl.
Yeah. So that depends on you. So how we define it. So in this case, it starts with 0 because we define it as 0. But if you do something like this, so for 1 to rows plus 1, then it will start from 1. So it's whatever you specify. It can start from both 0, 1, or something else. There's no default index.
There was another question if we can have Chpl highlighting in Vim. I tried it myself. I don't think we can do
Yeah, in Vim, I don't know. I don't use Vim, so I've never looked into this. So in Emacs, I'm using Emacs, and I think for Emacs, I actually had to download a plugin, a macro, to do highlighting in Emacs. So you'll need to Google it. In Vim, I don't know. In other text editors, some of them will do. Some of them, you'll probably have to Google that. So I don't know.
Looked up online, so there is a module for Vim which you can put into your Vim directory, and it will do it. But by default on Cedar, there is no syntax file. So you need to do it yourself so far.
Okay. Okay. Thanks, Dmitry. So next, we'll specify the initial temperature, and of course, we could do that in the same initialization line where we define T, but I'll just do it in a separate line. So I'm going to say T. And the reason I want to do it in a separate line is because I want to show you that you don't have, so I want to show you this syntax. So we're going to set the elements in the rows 1 to rows and in the columns 1 to columns, so not the entire. We're leaving out the perimeter. So the perimeter is going to be used for boundary conditions. So those indices, row and column indices 0, and then rows plus 1 and columns plus 1 are going to be used for boundary conditions. And the solution itself, so the internal mesh, is going to run from 1 to rows and 1 to columns. Okay? So I'm going to set that to 25 degrees. And because the variable has been defined as a real variable, so that's going to be 25 not integer, but 25 real value. Okay? And then so set the initial temperature. And now we need to learn how to do, so because we're going to run iterations, we need to learn how to do conditional statements in Chpl. So one way of doing that is to use the while statement. So while some condition, and I'm going to replace the condition with something meaningful in a second, while condition do, and then open curly brackets, the same as in C, and then inside curly brackets, have command 1, command 2, and so on. So that's one way of doing conditional statements in Chpl. So what we're going to do is we need to evolve our plate to equilibrium. So we're going to, first let me actually specify the initial value of delta. So delta, remember, is the temperature difference between the maximum temperature difference between two successive iterations. And initially, I want to assign it to some big number, so I can do something, 10 to the 38 or 10 billion. So what I'm going to do is simply use tolerance, let's say times 10. So make sure that it's just bigger than tolerance. Right? So some safe initial large value. And then I'm going to do the while conditions. So I'm going to run the loop while my iteration counter is smaller than the specified number of iterations. So that's the variable is equal to 500 right now. And delta is greater or equal than tolerance. Then do the following. So what we need to do is actually, let me erase this. And I will. So first of all, we need to specify boundary conditions for the temperature. And this is just a placeholder, so I will fill in these boundary conditions later on. But for now, I will just leave it empty, so I just want to indicate the things that we're going to have in the code. Then we need to increase the iteration counter by 1. So update the iteration counter. And then we need to compute T new from T. So this is a placeholder also. Compute T new from previous temperature, so from previous temperature. And then we need to update delta, the greatest temperature difference between T new and T. And then once all elements of T new are computed, we're going to pass them into T. So I'm going to say T is equal to T new. Right? And this is simply updating T once all elements of T new are computed. And then finally, I want to print T at the point I out, J out, every N out iterations or steps. Okay. So this is going to be the basic program structure. And then we'll keep adding things iteratively to this code. So for printing the temperature at the point I out, J out, we need to know how to do the if statements. And this is very easy. Like in any programming language, you simply use the if construct. So if condition, condition, then do some commands, perhaps in brackets here, then else, and do some other commands, and we're done. Right? So the usual if and else statements. And of course, you can also have else if. So what we want to do is check whether the iteration counter is divisible by n out steps. So we're going to say if the iteration counter, and then we're looking at the remainder of division of count by n out. So if the remainder is 0, that means it's divisible. Then we'll simply say write line temperature at iteration, temperature at iteration, and then count, and then I'll say column, and then actually print the temperature. I out, and then J out. Okay. So here we go. And also, I want to print this temperature right before I start the loop, so you can see the initial temperature as well. So something. So temperature at iteration 0 is equal to this value. So let's try to compile and run this code. And I'm gonna, for now, it's a very small problem, so I'm gonna compile it without the fast option. Oops, I have a syntax error, line 17, so I mistyped something. Let's see, line 17. I don't need a column here. So here we go. Okay, line 22. So obviously, when you type a lot of code, you will have typos, especially if you're doing it live. Okay, so here's the problem. because it's so 10 has to be either integer or real number. So you can either say 10 integer, or you have to specify a 0 after a dot. I'm not sure why exactly. You cannot just say 10 dot, so that has no meaning in Chpl. So I'm just going to update it, multiply by 10. Okay, let's try to compile again. Okay, it compiled, so let's try to run it. And it ran. And as you can see, so the temperatures are working with the matrix 100 by 100 to 500 iterations. So we run 500 iterations. But the temperature, because we're not computing it, the temperature is actually not computed. So it makes sense. So we need to update the temperature. So the line, the placeholder line, where we're computing T new from T, it actually has to be, well, the actual calculations. So we're going to do the for loops. We haven't seen the for loops yet. So actually, do this. So I'll keep adding lines here. So so we need to compute new temperature at every row and every column in the matrix in use. So we have to cycle through all rows and all columns. So let's cycle through all rows first. So I'm going to say for I in, so similar to Python syntax, 1 to rows, and I'm going to only go through the internal indices. So I'm not touching the ghost boundary. 1 to rows, then do, and then here we go, and then the same. So this is do something for row I, and we're going to do the same for all columns, all internal columns. For J in one of the columns, do, and then so do something for row I and column J. And then here we actually update the temperature. So this is the place where I'm going to paste that mathematical expression that we wrote at the very beginning. So computing T new from T. Okay. So T new at ij is equal to the average of the temperatures at the 4 surrounding points. I'm just looking at it to make sure that I don't have any typos. So I minus 1j, I plus 1j, and then ij minus 1, and ij plus 1. So it looks good to me. Okay, so let's try to, and also we need the second closing curly bracket because we have 2 nested loops. So let's try to compile and run it. Okay, compiled. And here we're running it. So now you can see the temperature is changing, and we are actually computing the right value. The reason I know this, so I out and J out is 50-50. That point is sitting right in the middle of our grid, and you can see that initial temperature was 25, and then it started decreasing because right now all our boundary conditions are zeros on all 4 sides. So we haven't implemented these fancier boundary conditions yet, right? So the boundary is 0 on all sides, and the initial temperature was 25 degrees, and then it's just cooling down. So you can see how temperature is going down in the center of the plate. Any questions so far? Okay, if not, then I have an exercise for you. So I'm going to paste this exercise into the notes. Yeah, question?
Yes, it's too fast. Sorry, we are running syntax, so it's too fast right now.
It's too fast? Okay, I will try to go slower.
Could you just wait so that everyone can compile, or I don't know?
Oh, sure, yeah, sorry. Sure, yeah. So I just pasted the exercise, and I will give you, let's say, 5 minutes on this exercise. It's really, really simple. And those of you who are still behind, you can actually use this time to do all the things we've done already. So the exercise is the following. What would be the temperature at the top right corner? So row 1 and then column cos of the plate. The border of the plate is in contact with the boundary conditions, so that's zeros right now. And we expect the temperature at this point to decrease faster at the in the top right corner than the temperature in the middle of the plate. So please modify the code to print out the temperature at the top right corner.
So, Alex, there is a question about semicolons. So when do you put the semicolon on the line?
So usually when you have a self-contained command that doesn't span multiple lines, so for example, update the counter, the iteration counter right here, or set a variable to some value. So a self-contained command that fits in a single line, then that command must always end with a semicolon. So in this case, in this line, while some condition do open brackets, we don't have a semicolon simply because this is a multi-line command that spans. So the actual block is huge, is what I highlighted here, right? So because the while statement didn't finish, that's why we don't have the semicolon here. But in general, every self-contained command that you already finished writing in that line must have a semicolon at the end.
So we don't place a semicolon after a curly brace.
Yes, exactly. So curly braces contain other commands, and then those commands will have the semicolons. Like every command here, so this command has a semicolon. Then this line doesn't have a semicolon because it opens a new loop. So here we have a new loop, and then the loop is, it spans multiple lines. That's why you don't have a semicolon for the loop.
This is similar to C or C++, by the way. So, and Marlene asked about some time to compile the code. So are you good now?
Very good. Okay, so if you manage to print the temperature in the top right corner, maybe you can place the final value, just copy and paste it into the Google Doc for everybody to see. And I'm curious about the values they got. So at the very last iteration, what is the number that you got? And since I don't see any values, I assume you're still working on it. So I'll give you a couple more minutes. So to help some of you, what I'm going to do now is I'll just going to paste and copy the entire code. Actually, if it's, I don't know, I'm not going to paste it into Google Docs because it might not show the caps and the spaces correctly. What I'm going to do actually, I will simply open permissions and we'll make it. We'll make the code. So I'm sitting inside the following directory: Cedar, home, Razumov, TMP, and then the code is called base Chpl solver. So what I'm going to do is I will simply open permissions. So make sure that I open permissions for my home directory for everybody to read, and then for all the files inside. So it's my TMP directory. So now you should be able to see the file if you simply do, let's say, cat on home Razumov TMP, and then the file is basesolver.chpl. So if you do cat on the file, you should actually see the file itself, and then you can simply copy it. If you want to use my copy of the file, copy it into your directory, right? So just run the following command: copy, path to my file, and then copy it into your current directory. If for some reason you way behind and don't have time to type everything, so you can simply run my code, compile and run my code. Okay, so I see some values. Excellent. Yeah, so that's the right value. Let me actually very quickly do this right here on the screen. So all you need to do is modify so I out and j out values while looking at so exactly what it was, top right corner. So row 1, columns. So I out should be equal to 1, and then column is columns. And then, of course, because I changed the code, I have to recompile it. So I'll say Chpl base solver -o base solver. We compile it, and then we'll run it again. And I see the value pasted there in the Google Doc is actually the correct one. So here we go. And as you can see, iteration, it takes about, I don't know, 3-4 seconds to run the code. So if we, for a change, if we compile it with the -- flag, it will run instantaneously compared to the previous run. Here we go. And the value is 0.063 and so on. So the temperature in the corner drops faster because the corner is next to the boundary with temperature 0. Okay. Any questions? Now, slightly more complex exercise. So I'll give you, I don't know, 10 minutes for this. I'm going to paste this exercise into the chat. Not into the chat, into the Google Doc. Right here. So exercise, and I shall spans 2 pages. So exercise 2, now let's have some more interesting boundary conditions. So suppose that the plate is heated by a source of 80 degrees located at the bottom right corner. So rows and columns. And that the temperature on the rest of the border on adjacent sides, so that's the bottom side and the right side, decreases linearly from 0 to 80. And the formula for that you can actually see in the slides. So if you scroll up in the Google Doc, I have a link to the slides, and you can download the slides and view the slide on your screen. So I will open the corresponding slide with the boundary conditions right here. So the boundary conditions, upper side and left side are still the same, zeros, and then the bottom side, so that's rows +1. And then columns, so spans columns from 1 to columns. And then the right side is, so now rows run from 1 to rows, and then the column is columns +1. So they are computed according to these formula. So basically what you need to do now is where we have to specify actually boundary for t, right here at the very beginning of the iteration loop, you have to add the formula to compute the values at the boundary, at the bottom and right sides. So I'll give you 10 minutes. This is slightly more complex. And then when you are done, just paste the last number, the last temperature that you get. So iteration 500, what's the temperature you get in the top right corner? 2 more minutes, and then I'll do this exercise right on the screen. Okay, so let's just do this quickly on the screen. So all we need to do is specify the boundaries on the right side and on the bottom side. So I'm going to type them here. So let's do the right side first. So we're going to go through all rows on the right side. So for I in 1, 2 rows, and then do something. And then here, so notice that we need to have curly brackets here, right? We don't need. We usually use curly brackets here, so we're going to type something like T, and then add row I, and then since it's the right side, so the column is the very last one, column plus 1, columns plus 1, and then we need to specify the mathematical expression here, so it's going to be 80 times I divided by rows. So 80 times I divided by rows. So here you have to be careful because right now we see that on the right-hand side we have all integers. So I, rows, and 80 are all integers. But you want to make sure that the result of the operation is actually real and it's not truncated. It's not the real from a truncated integer iteration, but it's the actual number. So you really want to do this calculation in real. So if you have 80 as a real number here, then the calculation will be done with all reals. So 80 times the column number divided by the rows number. So this is the right side. And then similarly for the bottom side. So because here we have just a single line inside the for loop, we don't need the curly brackets. So curly brackets are required only when you have more than a single command inside the for loop. So in this case, we have just a single command. So to simplify things and to make the code a little bit more concise, we simply delete those curly brackets. So, and the same for going through all elements in the bottom side. So now we need to cycle through all columns. For j in 1, 2 columns do, and then the expression is similar. So now we have the very last row, rows plus 1, and then the column j from the loop, and then we now have 80. Real 80 times j divided by the number of columns, and this is the bottom side, right? So that's it. That's all I have to do. So here we specify boundary conditions for the temperature on the right side and on the bottom side. And now let's try to run it. Compile first. And then run it. And as you can see, that made a difference, and that really makes sense because so initially, before in the previous run, we had all zeros on the boundary on all 4 sides, and in the top right corner, the temperature was going down to these values. So 0.06. And now we implemented another boundary condition on the right and bottom sides with a higher temperature. And that's why, that's why the temperature in the top right corner is decreasing, but not as fast. So now the final value after 500 iterations is close to 1 degree. Any questions? And again, feel free to copy the code. So I already told you where the code is. So at any point, you can simply copy my code. So it's a home browser on Cedar, TMP, and then base solver Chpl into your own directory. Okay. So let's do another exercise. The last exercise for, well, in this set, and then we'll go on to configuration of variables. So I'm going to paste the last exercise into the Google Doc. It's right here. So far, delta has always been equal to tolerance, which means that our main while loop will always run to 500 iterations. So let's update delta after each iteration. Remember where we had the line inside after we compute the new temperature. So here we have the line update delta, the greatest temperature difference between T new and T. So write a few lines to write the code to actually compute delta. And then optionally, you can print it out if you want. So I'll give you, I don't know, 5 minutes for this. And then we can do this together on the screen. And yeah, you can certainly have zeros on the other sides. So here we have, yeah, you can do exactly. So using this compact notation, so somebody just pasted into the Google Doc, that if you want to specify boundaries separately on the left side and the upper side, you can certainly do that. And because the answer is 0, so constant values for all elements on those sides, you don't need to have a loop. So you can actually have this compact notation, as you can see in the Google Doc. Okay, so the time is up. Let me quickly do this exercise right here on the screen. So what I'm going to do is simply compute delta, the greatest temperature difference between T nu and T. And because we're looking for the largest difference, we'll need to go through all elements and then compare the values of T nu and T. And then if that difference is bigger than delta, then we'll assign that value to delta. So first we need to assign 0 to delta. And then we simply cycle through all rows and all columns. For I in 1, 2 rows, do. And then curly brackets for j in 1, 2 columns, do. Open curly brackets. Then here's where we're going to use the temporary variable temp. So calculate the difference between T nu and T at point ij, but we need to know to use the absolute value, right? Because it could be positive or negative. So absolute value of T nu at point ij minus T at point ij. Close the absolute value, close that line, and then say if temperature is greater than delta, then delta is simply equal to Tmp, and then close the nested curly brackets. Okay, so let's run it. Let's compile and run it and see what it gives us. Okay, so no visible change, and that is because probably we need more iterations. So let's print out another couple of lines. So let's print out the number of iterations and the largest temperature difference between the last 2 iterations when after we finish iterating. So I'm going to add 2 lines here, and then the first line is right line is going to be final temperature at the desired position, and I'll actually print out the position as well. So I out, and then comma inside the quotes, G out, close square brackets, after, and then the number of iterations, and then say iterations is, and then I'll print the temperature at I out, J out. Oops. And then I'll also print out the delta, the latest delta. So right line, oops, the largest temperature difference was, and then I'll print delta. Okay. So let's again compile and run this code. Okay, so here we go. The temperature after 500 iterations at location 100 is the same value as we printed before. And then the largest temperature difference was 0.02. So that's why it didn't stop, because the value for tolerance is smaller than that. So the value for tolerance is 10 to the minus 4, which is obviously smaller than this latest value of delta. That's why we didn't stop before 500 iterations. So any questions right now? If not, then let's jump on to configuration variables. Here we specify at the beginning of our code, we specify a lot of constants, right? And then if you remember in the very first exercise, you had to change the value of I out and J out. So since you were changing these values inside the code, once you change them, you save the file. Then you have to recompile it and then run it, which is a hassle, obviously, if you want to change a lot of things and, just continuously monitoring how the code will perform. If you change, let's say, the problem size or number of iterations or some other constant. So recompiling the code every single time is obviously an annoyance. So normally in C or Fortran, how people do this, they will write a configuration file, input configuration file, and store all code parameters inside this configuration file, and then read the values of rows, columns, number of iterations, and so on from that input parameter file, so they don't have to recompile the code once again. In Chpl, there's actually a nicer solution. What you can do is use a configuration, what is called a configuration variable. So the idea is to have a variable that you can modify right on the command line when you run the code. So I'm going to show you an example. Let's say number of iterations is currently equal to 500. Let's change this line so that says constant number of iterations 500. Let's add a config keyword to it. So we didn't change anything else. Let's recompile the code and run it again. So again, it will run to 500 iterations because that's the default value. Okay. So by default, the code runs to 500 iterations. Now let's change that number right on the command line without recompiling the code. So the way of doing this is you specify the executable name, and then you pass the -- flag to it. So the flag is the variable that you're going to specify on the command line. So the variable is number of iterations, and then you simply assign a value to it at runtime. So here we go, and here we have 3,000 iterations. So once again, I bring up the command so you can see the syntax. Base solver -- variable is equal to and the value that they're going to use. So if you don't specify this flag, then it's just going to use the the existing value in the code, right? 500, and then you can specify any other value you want. So as you can see, if we run to 3,000 iterations, final temperature at the desired position after 3,000 iterations is this, and then largest temperature difference is roughly 10 to the -3. So we still, even after 3,000 iterations, we have not reached the design tolerance of 10 to the -4. So obviously, if you specify a even larger number of iterations, then at some point your code will stop. So this is called configuration variables, and really powerful construct in Chpl that you have not seen in C or Fortran. So let's do a quick exercise. Let's make all constant variables. So actually, the number of rows, columns, so the problem size, and out, how frequently you print out the temperature, and then I out and J out, the position at which you print the temperature, and then tolerance. Let's make all of them configuration variables. So I'm going to copy, paste that into the Google Doc here. So exercise 4, make rows, columns, and out, I out, J out, and tolerance configuration variables, and test the code simulating different scenarios. For example, change the problem size or play with a number of iterations and so on. What can you conclude about the performance of the code? I'll give you, I don't know, 3 minutes for this. Okay, so let's do this on the screen. So we want to make rows and the columns, the configuration variables. So the problem size is now adjustable from the command line. Then also you want to have, number of iterations is already done. And out is right here, number of how frequently we print the outputs. So that's also a configuration variable. Iout, jout, right here are configuration variables. And then tolerance is a configuration variable. So we should be able to specify all of them from the command line. Let's recompile the code. And let me run the following bigger problem. So instead of using 100 by 100 matrix, I'm going to use a 600 squared matrix. So I'm going to specify number of rows is 650. Number of columns is also 650. Also, I'm going to print the temperature at the following point. Iout is equal to 200, and jout is equal to 300. Then I'm going to run to 10,000 iterations. So number of iterations is equal to 10,000. And then I'm going to specify tolerance. So I'm going to use a larger value than before, 0.002. And also I'm going to change the frequency of printout. So n out is going to be every 1,000 iterations. Okay, so let me just run this. And now, as you can see, the problem is bigger. So instead of 100 squared matrix, we're running a 650 squared matrix. So it's taking a little bit longer to compute. As you can see, iterations are temperatures printed out every 1,000 iterations now, as it should happen. And since we specify a higher tolerance, the code actually converged after 7,750 iterations. And so the largest temperature difference was just below the specified tolerance, right here at the bottom. And then here's the temperature that we have in the desired location. So 200, row 201, and then column 301. We have these temperature. So fairly easy. And again, if you want to run a smaller problem size, all they have to do is simply adjust. Don't have to recompile the code, just adjust the problem size. Or if you want to print out every 3,000 iterations, that should work as well. So instead of printing every 1,000 iterations, so everything you specify as a configuration variable is adjustable from the command line. Any questions? Okay, so the last part of today's tutorial workshop is going to be timing code execution and then some concluding remarks. So the easiest way of, well, one of the ways of timing Chpl code execution is simply to specify the time command from the command line. So if you, in Unix, if you say time followed by any command, that will simply use the operating system to time the runtime. So in our case, so let's run it to 7,000 plus iterations and see what it tells us. Okay, so we have three numbers. What really interests us is the real time. So that's actual walk log time is almost 20 seconds, right? So 19.69 seconds. And this is how long it took for the code to run. And this is fine. But sometimes you want to time the execution of a particular part of your code. For example, we're doing a bunch of initializations in our code, and then we're running the loop. Let's say I'm interested in timing just how long it takes for my iterations. So from all iterations to run, not the initial variable assignment and so on. So let's modify the code. This is called, instrumenting the code. So let's insert some commands for timing the execution. So this can be done in Chpl by using the time module. And first, before you use it, you have to load the module. So you can actually load it not necessarily at the very beginning of the code. You can do it anywhere in the code before you use the variables inside that module. So the command to load a module is called use, and then you'll simply say use time to load everything inside the time module. And then we're going to use assign a initialize a variable right before, actually let me do it right before the start of the loop. So the variable is, I'll call it watch, and it's going to be of type timer. So that type is a class, obviously, is provided by the time module that we just loaded. And this variable has a number of built-in functions or methods. And then one of the methods is to start the timer. So we can say watch start, starting the timer right before the loop. And then we also need to stop the timer. So right after the end of the loop, we're going to stop the timer. So watch stop. And then we need to print out how long it took for the well, between the start and stop statements. So I'm going to say right, the simulation took. And then I'm going to use the same variable, and there's another method called elapsed, which simply gives you the difference between the in seconds between the start and stop commands, and I'll say seconds. Okay, so let's again compile it. And then let's run it. So I'm just going to do exactly the same problem as before, 600 squared matrix. Timing. Oh, actually, sorry, I don't want a type command, right? I'm just running the code itself. So without the time command, I just run the code itself with all those variables specified at the command line, and then timing is happening inside the Chpl code. Okay, so the simulation also took 19.5 seconds, similar to previous estimate, and this is how you time the well, individual code blocks inside Chpl. So final exercise for today, and then after you do this exercise, I have some concluding remarks. So the exercise I just pasted into the Google Doc. Try recompiling without fast and see how it affects the execution time. So specifically what I'm interested in is what is the speed factor when you include -- fast option when you compile the code. And it's going to be a big factor. So if it takes a very long time to run the large problem without optimization, then try to reduce the problem size. But I'm interested in that factor, so the numbers that you'll get. Runtime with and without code optimization when compiling. Okay, so I'll give you, let's say, 5 minutes. And then if you have the number, paste it into the Google Doc. And then we'll discuss it. So I see somebody already pasted the answer. So for the default config parameters, so a fairly small problem, the difference was not that large. So try increasing the problem size. And I'm going to do this on my screen as well while you're doing this. I also want to measure this number. Okay, so I see some numbers here pasted into the Google Doc. 3 seconds with fast, 9 seconds without, so a factor of 3. And then a factor of 20 on a problem, somebody else on a problem 200 by 200. So factor of 10 or 20, well, somewhere in that ballpark. So I did the run for right here on my screen. So I used the problem size 150, 150, and then specified tolerance 2 times 10 to the minus 3, printing out every 100 iterations, and then a maximum number of iterations 10,000. So 150 squared. It took me 63.994 seconds to run it not optimized, and then half a second to run it optimized. So I just divided the two numbers, and for me, the difference is a factor of 130, which is a big factor. So this is, oops, I'll just type it here. So what I got for 150 squared problem, a factor of 130, which is actually huge. And when I was preparing this workshop, I did this run several times, and I always getting the number of an order of 100. So it's a fairly high number, and it's higher than what you guys, well, the two answers I see here, so not sure why they're so different. But for sufficiently large problem, you should see a substantial difference. So it's a difference of, in my experience, it's about a difference of this problem is about of an order of 100, which is actually a huge deal. So if you spend, just all you have to do is specify the optimization flag, and it takes a few seconds longer to compile, but then in the end, your code runs 100 times faster. It's actually a huge deal because, you wait for a few minutes instead of waiting for a whole day. So, so big difference. So make sure that whenever you run any heavy codes, CPU-intensive codes, large calculations in Chpl, make sure that you specify the -- fast flag when you compile the code. Okay, so that's the important bit here. All right, so that's all I have for the materials. Are there any questions for serial Chpl? So the basic language features that we covered. We did not cover quite a lot of stuff, and that is simply because I did not have time, and lots of things like iterators, functions. So I did not mention functions, but you certainly can have functions in Chpl. So functions are called procedures in Chpl. I guess that comes from Fortran. And you can parallelize functions, and there's actually quite a lot of interesting stuff there. But this is not essential for the problem that we're doing right now. I mean, for the heat diffusion problem that we're solving. And functions, we're not going to use them in the parallel sessions next week and the week after, simply because it's another layer of complexity. Certainly very useful to know how to write functions in Chpl code, but it's just not something we're going to use in this workshop. So same for iterators, same for some other things. So simply no time and really no point in covering them here. If you're interested in learning how to do functions, iterators, other things in Chpl, then just hit the Google the Chpl documentation or follow the links that I specified in the slide. So I still have several questions here. So is there a list of available modules that can be used in Chpl? So somebody posted the answer. Is it similar to interpreted or compiled code? So yes. So Chpl is a compiled code. So that means that you create executable right before writing the code. So you can build your text Chpl code into a machine executable, and then you run it. So the difference between optimized and non-optimized code is not the same as the difference between interpreted code and a compiled code. So Chpl code is always a compiled code. But when you compile the Chpl code, the same goes for C, Fortran, any compiled language. When you compile the code, there are lots of optimizations that a compiler can do. And these optimizations are expensive in the sense that it takes longer to produce the final executable, but sometimes they really pay off. And in this case, as you can see, Chpl really does optimization in Chpl. In the compiler, really does a splendid job in accelerating the code. So it's not the difference between, running with and without fast is not the same as running interpreted and compiled code. It's more of the differences between a badly compiled code and a well-compiled code. So, yeah, different optimization levels. Are there any other questions? Okay. So the last thing that I want to mention is, before I let you go, is it's actually somewhere, yeah, right here. It's in the Google Doc at the top. You can run, so I didn't mention this, but you can run Chpl on your laptop as well, and there are several ways of doing this. So if you're on a Mac, then you can simply install it via Homebrew. Simply install Homebrew and Google what it is, and then you need the only command, brew install Docker, and that will install Chpl on your laptop, so you don't have to use Cedar for these simple exercises. And that will give you a single locale Chpl. So you'll be able to use multi-core parallelism, but because you still have a single laptop, single node, you will not be able to run distributed memory code. So they will simply not run on this installation. So another option is, and this is really, really interesting. So you can install, if you use Docker, you can install a Chpl Docker container, and that simulates a multi-locale platform. So it actually simulates a computer cluster. I'm not sure exactly how they do this, but you can run either single locale or multi-locale parallel Chpl codes all inside this Docker container on your laptop. And that is really fantastic for code debugging and for doing these sort of exercises, even for distributed memory codes. So obviously, when you run a multi-locale, so multi-node Chpl code on your laptop, it's not going to run any faster than a single node Chpl code, simply because you are simulating, well, you're emulating a multi-node cluster environment still inside your laptop, so it's not going to run any faster. But obviously, when you run such parallel multi-locale Chpl code on the cluster on Cedar, it's going to run faster, as you will be able to see next week and then the following week for distributed memory codes. So that's all I have today. Tune in next week. So next week we'll actually start writing parallel code, and this is really, really interesting. So we'll study the basic concepts, and then actually let me bring back the slides with the program. So we'll study various task parallelism, various concepts in Chpl of organizing task parallelism, and then we'll talk about concurrency versus parallelism, concurrency versus locality. Really, really interesting discussion. So if you've never heard about it, then tune in next Wednesday, March 7th, and we'll do an interesting session. So next week, shared memory parallelism. And then the following week, March 14th, we're going to do distributed memory parallelism. So thanks all. I'll stick around for the next few minutes, and you can always ask me questions. My email later on, by sending me an email. So my email is alexrazumov@westgrid.ca. So thank you.